Consider the Verilog module shown below. How many input signals are specified? So we've got clock, reset load, and seed. So 1, 2, 3, 4 input signals. Although it's a little confusing though, because seed is 8 bits. So if you were counting bits, it would actually be 11 bits. But it's 4 signals, because one of the signals is 8 bits. Consider the following system Verilog module. Assume the module is reset with a reset pulse at the start of execution. What's the value of state in the first 3 cycles after the reset pulse? So when you reset it, it sets state to be 1, 0, 0. After it resets, the state will update on the rising edge of the clock. And these variables, state, so this is the part that's a little misleading here. State is the current state, but when you're setting state, you're setting the next state because you're using, well, in this case, you're using these non-blocking assignments. These assignments to state won't take effect until after you're finished evaluating the always. So to figure this out, the easiest way to do it, I think, is just to have a table where you start out with state 1, 0, 0, which is what it resets to, and then you just run through the logic here to calculate the next state. And once you've calculated the next state, you then bring it down to the next row of the table to make it the current state. So this is the second column is the current state, and then I've got it split out into its 3 bits on the right 3 columns, and that's the next state. So if the current state is 1, 0, 0, the next state will be, first bit will be 0, and by first I mean bit 2, leftmost bit, most significant bit. The second bit, bit 1, will be whatever the first bit was in the current state. So that was 1 here. So state bit 2 is 1, so the next state bit 1 will be 1. And then the next state 0, the last state bit, is current state 1 or current state 0. So we're just going to do an OR of the rightmost 2 bits. So that'll be 0 or 0 is 0. So now you've got 0, 1, 0 will get carried down to the next row, and that will be our next state value. And so then you repeat the process. The next state the next state bit 2 is always 0. The next state bit 1 will also be 0 because state bit 2 in the current state is 0. And the next state bit 0 will be 1 because we're ORing together the first 2 bits in the current state. Make sense? Yes? In terms of the next state? So I think what will end up happening is that cycle 1 starts out as 0, 1, 0, and it becomes 0, 0, 1. But I think at that point, it's probably just going to lock in at 0, 0, 1 and just stay at that value. Up here? Yep, right here. This line? Oh, so this is saying the next state 0. And by the way, the reason I mentioned this was a little confusing is because when I'm saying next state, I mean, there's only one variable called state, right? But the next state is what's being set on the left-hand side of the assignment, right? And the current state is the stuff on the right-hand side of the assignment, right? Because in Verilog, these guys are separated based on the behavior of the always, right? So the always will run. After the always gets done running, it'll set up the new state, right? But it's always going to be looking at the old value and then setting a new value, right? So when I say next state, I'm really talking about state, right? But it's what you're assigning state to be, right? Just to clarify that. So in terms of this line, you're asking about this line of code. So this is taking states, the current state 1 and the current state 0, which are these just the right 2 bits over here in the table, right? and it's doing a bitwise OR, just an OR operation. So if either one of those got, in other words, if either one of the bits in state 0 or 1 are currently 1, right, then it will be 1, then state bit 0 will be 1 in the next cycle. Okay, so, and I think what will happen is once you get the state to 0, 0, 1, it'll basically always be that way, because it'll stay at 0, 0, 1, right, in steady state, because every new state value will put a 0 in state 0, or I'm sorry, state 2, sorry, right? So the first bit of the state will basically always be 0 after the reset, right? Because when you reset it, it's 1. But after the reset, the first cycle after reset, you're going to set that bit to 0, and it's going to just stay 0. And then state 1 is going to get the previous value of state 2. Well, that means by the second cycle, that bit will always be 0, right? It's because basically state 1 is the same as state 2, but just delayed by 1 cycle. There's an extra cycle of delay. So it takes an extra cycle for state 1 to catch up with state 2. So it takes 1 cycle to get state 2 to 0. It takes 2 cycles to get state 1 to 0, at which point they will always be 0 forever until the next time you reset. And then state 0 is going to be will basically just be 1, because I guess starting from cycle 1, it'll go to 1 and stay there, because it will just be whatever the previous value of state 0 was, right, which is 1. Make sense? Now, when you write a state machine, I think I showed how to write a state machine, a finite state machine in Verilog. A lot of times they'll be written where you'll actually have a variable called next state. So you'll have in always a combinational logic that'll set the next state, and then you'll have a clocked always that'll transfer the next state into the current state, right? In this case, they're kind of merged. Those two things are merged together into one always. So I'm calculating the next state and then clocking in the next state in the same always block. And that's the reason why it's a little difficult to read, because the next state and the current state are the same variable state. Okay, this one says give the value of the signal A in the first 3 cycles after reset. So this is a similar one. We're going to reset this one to 1, 0, 1. And now this is the only curveball here is that I've got this one statement that uses a blocking assignment, which means that basically what you're doing here is, because this is blocking, the second line of code is going to see the impact of that first line. So it's equivalent to making this kind of a macro, where if you were to take this sub-expression, you could transfer it right down and substitute that for A in the second line. So basically what's happening here is on every cycle, you're going to shift A 1 bit to the left and XOR it with 1, 1, 1, which just flips all the bits. So basically shift by 1 and flip. And you do that at the same time. So if you take this guy, 1, 0, 1, on the next cycle, it's going to shift 1 bit to the left. So 1, 0, 1 will become 0, 1, 0. And then you're going to flip. So 1, 0, 1. Right? And so what will end up happening is that it'll just stay 1, 0, 1. Because if you take 1, 0, 1, you shift it 1 bit to the left and then flip it, you get the same thing. So you'll just get an endless sequence of 1, 0, 1s. Okay, this one, what is the problem with the following code? A equals A plus 1. This is a very common thing to do. This creates a counter, right? The only problem is that it's in an always comb. It's not a clock. For this to be a counter, you'd want to synchronize this to the clock. So you'd want to have always at pos edge clock there. Otherwise, this creates a dependency that doesn't have a flip-flop, right, in the loop, in the feedback loop. So this will end up just incrementing. It'll become unstable, right? This will become a sequential logic circuit because it's cross-coupled basically. The output feeds directly back into the input without that flip-flop in there to control it, right? To make it only update every cycle, right? There's nothing that's controlling this. It's just.
It's not clocked, so it wouldn't even.
I don't know. It would create like an oscillator probably. It would just run so as fast as the propagation delay in the circuit would allow it to run. But it wouldn't be stable. I mean, in other words, it would be hard to predict how this would behave because it would depend on the speed of the circuitry that it's.
But also that you can't synthesize it then.
That's a good question. Probably right. It'd probably give you an error if you tried, but I'm not 100% on that. It might synthesize it. Okay, what are the first three values of A generated from the snippet below? This one is, again, another one, basically a sequential logic circuit, clocked sequential logic circuit, synchronous sequential logic, I should say. Because sequential logic just means that the output is a function of the inputs and the history of inputs. And then synchronous sequential logic means that there's a clock involved in there too. So this one also has some bit twiddling or bit manipulation with the curly braces. So in this case, the value of A will be updated by taking whatever was in the least significant bit of A, concatenating with that with 2 copies of bit 1, and then concatenating with that with a complement of bit 3, and then finally complementing that with the prior bit 2 XORed with bit 4. So does that add up to 5? It's supposed to be 5 bits, right? A is 5 bits? Yeah, A is 5 bits. It's declared as 5 bits. It's initialized as 5 bits. And then you're hoping that this all adds up to 5 bits, hopefully. So that's 1 plus 2 is 3, plus 1 is 4, plus 1 is 5. So it just, luckily, this concatenation thing, when you add up all the bits that you're concatenating, works out to be 5 bits.
What if there was an extra? Would it just truncate the end?
I think it would truncate the beginning, the most significant bit is my guess. But it would give a warning. Yeah. But you might miss that warning because there's a lot of warnings that you get when you synthesize. So in this case, I built my table, but I grouped the table, or I split the A by bit to make it easier to read. And then for the next A, I split it into the groups mapping to this thing, to the concatenation. So I've got the next bit 4 is the current bit 0. So this bit 0 is just going to transfer into in here, right? So basically this column, these 2 columns are always going to be the same, right? And then A 3 down to 2. Now notice there's no 3 down to 2 in here, by the way. This 3 down to 2 I inferred from the way that these are concatenated, right? Because I know I had 5 bits here, so the first bit must be 4. And then because there's 2 bits, tacked on, that must be 3 down to 2. And that's bit 1, and that's bit 0. So bit 1 is, bit 3 down to 2 is always a duplication, so the 2 bits are the same. And it's going to be whatever the complement of the bit 3 was. So this is going to be, did I screw that up? Bit 3. Bit 1. 2 copies of bit 1. Yeah, so bit 1 was 0, so you got 0, 0. Here bit 1 is 1, so you have 1, 1. Here bit 1 is 1, so you've got 1, 1. Yeah. And then the next one, which is bit 1, is the complement of bit 3. So whatever you have here is going to be complemented. So that's a 0, so you have 1, 0 here, you have 1 here, 1 here, you have 0 here. And then finally the last A0, last bit, is you have to look at A2 and A4 and do a XOR. So 1 XOR 1 is 0, 1 XOR 0 is 1, 0 XOR 1 is 1. Okay, any questions? So this to me is kind of the most important thing to understand about Verilog, is how these sequential sequences work. That's just my opinion, though. But it's a very common thing to have, when you write Verilog, is these sequential logic. Okay, so quiz 6 was a radical shift to control theory. And so now we're going to talk about differential equations. So the question here is, which of the following is a LTI? That stands for linear time invariant system. So linear time invariant system is, it's a really strange term because normally when you think of linear, you think of a straight line. But differential equations are not straight lines at all. The reason why they're called linear is because they're restricted to only having signals being a time series function, right? They're restricted to having the time series functions and their derivatives and their integrals multiplied by linear terms, coefficients, right? Just a constant. So in this case, this one is not linear because we've got the derivative of g divided by the g. That's not allowed in an LTI. I mean, you can do that in general, but it's just it would not be a linear time invariant system. In this case, we're multiplying derivative of g times g. That's not allowed. Here we've got the derivative of g. It's negated, but that's fine. It's just because we're multiplying it by -1. And then we add it to 2 times g of t. So this one's good. I think this one's fine. And this one's no good because we're squaring g. So the answer is the third option. This is the only linear time invariant system. And then which of the following is the S-domain form of f of t equals the derivative of gt relative to t? So now in this case, by the way, I should also mention that these differential equations, whenever you do a derivative or an integral, it's with respect to time. So if you're doing a derivative, that's just equivalent to multiplying the S-domain form of that signal by S, right? So it's just SGS, right? Notice though that you capitalize the variables by convention. It's no longer time domain, it's frequency domain. So the variable is S, and you basically just say SGS. That's really simple. Yep. That's the first time I saw this too, is in circuits too. Which of the following is a method for determining if a system is stable? Check if the order of the denominator polynomial of the transfer function is 2 or less. No, that's just made up. Check if the numerator of the transfer function is non-zero. No, that's just made up too. Check if any poles of the transfer function lie in the left-hand plane. This one is close to being right, but the key word here is any. It has to be all. Yeah, if they're all in the left-hand plane, then it's stable. And then check if the impulse response is bounded. That's the answer. That's not the only way to tell, but that's one way to tell. Which of the following are valid eigenfunctions of the transfer function 1 over s squared minus s minus 56? So to figure this out, you have to just do some algebra. So, and this doesn't always work. This only works in special cases. But in this case, it works because you can factor the denominator to be 1 over s minus s times s plus 7. So I just factored that. And then I want to break it into the sum of two fractions where the denominator is a polynomial of s, but only a first-degree polynomial. And the reason I'm doing that is because when you have it in this form, you can directly do an inverse Laplace transform. If it's in this form, you can't directly do an inverse Laplace transform. So then I do the trick where you basically just solve for a and b. And this is kind of wild because normally you wouldn't be able to solve for a and b, right? Because you just have one equation and two unknowns. But this is a special case where you can use this trick where if you look at this form, you find the common denominator, which is s minus 8 times s plus 7. And once you do that, you can put it in this form. And then if we assume that the numerator is -7, then it eliminates a as a variable because it zeroes out this a. So then we're just left with one equation and one unknown with b in it. So let's just assume that s is -7. And so if that's the case, if s is -7, then we have 1 equals b times s minus 8. And if we assume that s is 8, then likewise we can eliminate the b because 8 minus 8 is 0. And so we can solve for 1 equals a times s plus 7. So then we can solve for b and a. B is 1 over or -1/15, and a is 1/15. And that's weird how that worked out, but okay. And then, yeah, and then we have a and b, and then you can substitute those back in, and then you end up with 1 over 15 over s minus 8 plus -1/15 over s plus 7. And once it's in this form, then you can convert each one of these to eigenfunctions. These are both so the inverse Laplace transform of that are exponentials. So in this case, we're now going from S domain to time domain. So, and this comes just from a table. This is a table-based solution. You look at a table of inverse Laplace transforms. And this is one of the simplest one in the table. So this is 1/15 times e to the 8t minus 1/15 times e to the -7t. So this ends up being unstable, which makes sense because the poles here are -7 and +8. Positive 8 is a right-hand plane, so this is unstable. So if you give this an impulse, it just blows up, basically. And this is what you'd get if you did an impulse. This actually gives you the impulse response directly, these eigenfunctions. And the reason, and you might say, why is that? The reason for that is because this actually ends up being a transfer function. The impulse is 1 in the S domain. So you're basically taking 1 times that to chain together the impulse as the input and then the transfer function here. If you want to do a step response, then it's a little bit more complicated. Usually, the impulse is easy enough to do it by hand. If you want to do a step response or a sinusoidal response, then you might as well simulate it. It's harder to work out by hand.
When you were just looking at the eigenfunction, how could you tell it was unstable?
Oh, because the poles. Well, it's a good question. The poles, and in the time domain, this exponential is going to blow up as you. So you basically.
Beat the other one.
Yeah.
It's an 8 versus a 7.
Okay. You're finding the limit here as t goes to infinity. So you're taking this function, and it's a limit. Limit as t goes to infinity is infinity.
Okay.
That's the reason I knew from that why it's unstable.
Exactly.
Okay, what's the transfer function resulting from feeding the function 1 over s plus 1 into the function s over s squared? Well, the transfer functions are cool. You just multiply them together. So if you want to feed one into another, you just do this. The problem is, though, that if you guys were ever take a control theory course or a more advanced controls course, they might cover this, but only like on the first day of class, because this is only a 1 input, 1 output transfer function, and most practical control systems have multiple inputs, multiple outputs. But this just shows you a simple, 1 input. Now you might say, what if you do have more than 1 input, 1 output? Well, then you need a matrix of you need an S domain matrix, basically, to represent that. And most people don't even do that. They use state space modeling. They don't go to the I don't think so, at least in my experience, usually. But anyway, if you're in the S domain, this is a nice toy problem in the S domain: 1 input, 1 output. Okay, and yeah, okay. Now this one I got the idea of this with I was swinging my kid on the swing set, and I was thinking about how monotonous that is, and I thought it would be cool if you could just design a device that could just swing your kid on the swing set automatically. Like you could set a set point where you wanted to swing them so high, and you could just set that set point, and then it would just automatically do it, right? So you're designing a cyber-physical system to counteract the movement of a regular. Actually, this one's counteracting. This is actually trying to stop it. This is the opposite. But for this, you need to model the physical system for your plant, which consists of a hanging pendulum whose angle is theta t. So theta t is the signal or the time series variable that represents the angle of the pendulum, right? So it's just going to go back and forth. So if you looked at it on a plot, it would be like a sine wave, basically. And then the input is a force, F of t. So the time domain equation, this is actually the real equation for a pendulum. Of course, ideal pendulum, no air, no resistance, no friction, no friction in the system. Oh no, I do have friction. I'm sorry, I take that back. B, I do have a friction term. That's the B. So it's F of t plus the second derivative of the angle equals negative B over m, where B is the friction, m is the mass of the pendulum. And then multiplied by the first derivative of the angle minus g, which is gravity, over L, which is the length of the pendulum. So this is the, oh, and then multiplied by the angle. So it looks complicated, but it really isn't. It's just the physics equation for a pendulum, basically. And so if that's what you're controlling, you would define that as the model of the plant. Why do you need that? Because it helps you design the controller. Otherwise, how do you design the controller if you don't have a model? It's trial and error, maybe. Which, to be fair, is what we're doing in Lab 4. For this class, we're just using trial and error because we don't have a model of that motor in Lab 4. I tried to build one, but I failed miserably at that. But in this case, we have a model of the pendulum. And so I'm not even asking you to design the controller. I'm just saying, what's the S-domain transfer function of that function? So just convert that to S-domain, which is pretty simple. You just start with that, and you're just converting. Remember, you're converting the derivatives to just S. Second derivative is S squared. And there's no integrals here. So yeah, just derivatives involved here. So capitalize F, capitalize, oh, I guess I didn't capitalize theta because it was already capitalized. So yeah, the derivative just becomes, second derivative is replaced by S squared, first derivative is replaced by X, and then if you don't have a derivative, then it just goes from T domain to S domain. And then everything else stays the same. So that one's just a direct translation. Oh, I'm sorry. And then the final thing is I asked for the transfer function. So the transfer function is, if I ask for a transfer function, that means I'm looking for a ratio of the ratio of the output relative to the input. So we're looking for theta over F because we're putting a force in and then we're getting a theta out, right? And so you have to restructure this so you can get it as a ratio of theta over F, and then that should give you a ratio of just two S polynomials. And so yeah, I just factored out theta S, and then once you factor out theta S, then you can just divide by F of S. And so you get that. And yeah, I think that's already good to go, right? Yeah, it's the ratio of, so it's negative 1 over S squared plus B over M times S plus G over L. Yeah, so it's just a matter of getting the right form. Like I said, transfer function is when you assume there's inputs and outputs, but there really aren't inputs and outputs, but we want to treat it like there's inputs and outputs, so you just get it into that ratio form. And what's the S-domain transfer function of the PID controller with the proportional constant 2, the derivative constant 1, and the integral constant 4? Well, that's easy. It's basically just 2, so it's Kp with nothing, plus the derivative times S, so just S, plus integral multiplied by S, 1 over S, which is the integral. So this is just another example of going from time domain to S domain. And then you could, normally, the problem here is this S to the negative first power. So you can multiply this times S over S, and you can get it into a form where you have no negative exponents of S. Oh, yeah, sorry. animation order was wrong. Okay, and then what's the Tustin transform of transfer function f of s over y of s equals 1 over s squared plus 1 with t equals 1. So this is, Tustin transform is when you go from continuous to discrete. So you can't really design a real continuous anything on a computer. Everything is discrete. But when you do the conversion, you have to pick a sample step. Yeah, you have to pick a time step. In this case, I just said 1 second. So the Tustin transform is pretty cool because it just gives you something as a substitute for S, and you end up with a Z domain. Z domain is the discrete version. The problem with this is that even though this looks simple, when you start substituting in, it gets complicated fast. So I tried to fix something. I tried to find something that was simple as I could, but you can see that it starts to get complicated, and then you have to work it out. You have to go through several steps to get it into, the transfer function form, right? The ratio of polynomials of z. Now the question though is, you look at this and you're like, holy cow! You're telling me I went from this, which was really simple, to this, which is looks a lot more complicated, and that was with just a 1 second time step. And it's like, yeah, I mean that's how it works out with this. Now you might say, wait a minute. Now what if I want to go to time domain here? How do I go to time domain? Well, you can't actually go to time domain directly from this form. You would have to get it into another form where you basically had, you're calculating f of t, you'd want to isolate f of z on one side, right? Because that's your output. And then on the right-hand side of the equation, you can have f of z's and y of z's multiplied by z's, as long as all the z's are 0 or negative exponents, because that basically means the past. Anytime you have z with a negative, that's the past sample. Z negative 1 is the last sample, z negative 2 is 2 samples ago, right? And so it basically just takes some algebra to figure that out. But once you have it in that form, then you just say that anything that's z to the negative n times a value is just that signal value that many samples ago where you use the exponent. So by the way, you can see why most people that do this in practice, they use tools. They use MATLAB Simulink to do all this, to work all this math out, because this gets complicated. It's hard to do this by hand. Okay, and what's the closed loop transfer function for the system below? So in this case, I have 3 transfer functions that are connected in series with the classic closed loop, where I've got R as the reference, or as the set point, and error is the error. Error is the difference between the set point and the actual operating point. We're trying to make this 0. So what is the closed loop transfer function? Well, this is just a rule of thumb. The closed loop transfer function is the open loop transfer function over 1 plus the open loop transfer function. And I showed the derivation of that in class. And the open loop transfer function is just f times g times h, right? You just multiply those guys together. So it's just that. Now, of course, if these were all, described in the S domain, you'd have to actually multiply them all out, and it would get ugly. What's the discrete time implementation of the transfer function? So time domain. So how do you figure this out? Well, like I was saying before, you basically have to get it into a form. It takes several steps. The key thing to understand here is that, remember, f is the output, g is the input. So we got to get f by itself, because we want to calculate the next output from our controller is calculating the next output. The function that it's using for that, it can be a function of the outputs. You might say, wait a minute, it's calculating an output and then it's using its own output as an input to calculate the next output? Yeah, I mean, that's what we did in Verilog, right? When we were doing the state thing in Verilog. It was the same thing that we're doing in the Verilog stuff. Actually, though, in the Verilog, when we did it in Verilog, we're always looking at the last cycle, the last step, right? In this case, you could go back. In this case, you're looking at f of t 2 samples ago, 2 time steps ago. Okay, but anyway, that's just a matter of working it out. And okay, I think that's the end of that. Okay, good. Let's move ahead to quiz 7. Okay, this was on real-time scheduling. So this is a, hopefully it's obvious why we've combined these topics together, right? Real-time scheduling has a time step. The time step is the deadline now that we're talking about. We have to meet these deadlines. So we have to calculate, the function I just showed you would have to have been completed by the time step, right? We're hoping to do this calculation in the time. You might say, well, come on, man, you just did a couple of multiplies and adds. Computers can do that fast. Well, yeah, but you have to keep in mind that normally you have one processor. If you have a robot, you're controlling every single, actuator on one processor. You're time division multiplexing the processor. You're not going to have one processor for every actuator. You're going to have, right, generally, you're going to have one processor that's going to run a whole bunch of loops, control loops, right? And then you have to run that with a real-time operating system. And where do you get that? Well, you have to buy it. That's something, people always ask me, Quartus, is there an open source version of Quartus, like a free version? No. Same thing with real-time operating systems. There's no open source real-time operating system.
There's a whole bunch of Linux this way we could get.
They claim they're real-time, but they're not. I think they're soft real-time generally. And the ones, and I have seen ones that they build hard real-time on top of Linux, but then they sell that, Now, Linux does have real-time features in it, but it's still not, it doesn't make guarantees. You can set the priorities, basically, and you can tell the scheduler when the deadline is. You can even, and I've done that. But the scheduler is not going to do the calculations necessary to know if it can guarantee that it'll make the deadlines. That's the difference. You need to pay big bucks if you want that. So assume that you have 4 tasks with, there is one called FreeRTOS, by the way, a simple one, but it's designed for really lightweight microcontrollers. Anyway, assume, and one more thing. When I say real-time operating system, I'm not talking about something that you get a prompt. There's no login, there's no prompt. Real-time operating systems are not like Linux generally. They're just libraries that you statically link with your executables. They're not interactive usually, right? Anyway, but assume 4 tasks with execution time period values of 415, 520, 625, 730. I didn't give the units, but I assume those are like milliseconds, right? Something like that. What's the utilization? Well, you just add up the fractions there. Turns out that would be a 99% utilization to put those 4. That would be tough. What's the RMS bound? Well, the RMS bound is just the equation I gave in class. The RMS bound is 2.42. Since that's greater than 2, we can't guarantee this will work with real rate monotonic scheduling, RMS scheduling. It might, or it might not. But if you're under the bound, it guarantees it is schedulable. If you're over the bound, maybe, maybe not. We don't know. There's no way to know. You could say, well, you could run it. Yeah, but you don't know how long you'd have to run it for before it would potentially miss a deadline. Could be a long time. So yeah, so this one we don't know. It doesn't meet the bound. Assume 3 tasks. Are they schedulable RMS? It turns out that they're not, because they don't meet the bound. And now you might say, wait a minute, it didn't meet the bound, but you said that that doesn't guarantee they can't be scheduled. Right, but also if you calculate the utilization, it's over 100%. So yeah, definitely cannot be. That one's for sure can't be scheduled with RMS, not on one processor anyway. What happens if you have 2 processors though? So assume you have 4 tasks. You have 2 processors this time. Are they scheduled with partitioned RMS scheduling? Okay, partition means that you assign tasks to processors, right? So how does that work? Well, unfortunately, you have to fully enumerate. So if you have 4 tasks, I can put them all on one processor, in which case I get an RMS bound of 3.73. I could put 1 task on processor 1 and the other 3 on processor 2, but every single way to do that gives me a violation of the RMS bound on processor 2. So that would be 1, 2, 3, 4, those 4 rows. I could put 2 tasks on one processor and 2 tasks on the other processor, and there are 3 ways to do that. So I can put 1 and 2 and 3 and 4, or 1 and 3 and 2 and 4, or 1 and 4 and 2 and 3. It turns out that the only one that works is if I do 1 and 4 on one processor and 2 and 3 on the other, in which case they both meet the RMS bound. All right, so I had to look at every possible way to partition it, which obviously you can see why you don't want to use partition scheduling. Assume 3 tasks. Under which algorithms are they schedulable? Well, the utilization is less than 100%, so EDF would work, earliest deadline first. The RMS bound, unfortunately, doesn't meet the RMS bound, so RMS only? Sorry, that's wrong. EDF only. Sorry, should have said EDF only. Earliest deadline first will work. As long as your utilization is less than 100%, earliest deadline first will always work. But no one uses that because it requires that the priorities constantly be recalculated. It's dynamic priorities. Assume 4 tasks. What's the largest value that would make them schedulable with rate monotonic scheduling on 2 processors? Where n, I've got a variable n in there, so you just have to basically use the equation I gave you where it's the utilization must be less than or equal to 2 times basically 0.41. Square root of 2 minus 1 is about 0.41. Actually 4142, I guess. And then you double that, so 8284. So the utilization has to be less than or equal to 0.8284, which it would be as long as n is less than 5.11. But I think on the quiz I assumed it was an integer, so it was 5, rounded down to 5 on the quiz. Assume 4 tasks. Are they schedulable with EDF on 2 processors? Okay, this one is weird. You have to calculate the greatest common divisor of the periods, which in this case is 4, and then you multiply that 4 times the utilization of each individual task, and you're looking for that to be integers. And in this case, unfortunately, they're not integers. You end up getting fractional numbers, so possibly not. And how many possible ways can 5 non-periodic tasks be scheduled, assuming they're all ready? Pretty much just 5 factorial, 120. These, by the way, non-periodic, right? That makes it a lot easier if they're non-periodic. If they're periodic, then I can't even imagine how many ways there are to schedule if they're periodic, right? Because they're constantly getting reissued. Okay, what statement is true? RMS requires dynamic priority. That's not true. RMS requires static priority. That's true. EDF and RMS require static priority. No. EDF requires static priority. No. EDF is dynamic, RMS is static. So it's static. Yeah. Okay, which statement is true? Any task having utilization that meets the EDF bound will also meet the RMS bound. No, it's not true. Any task that could be scheduled in 2 processors can be scheduled in 1 processor. I don't think that's true. Any task that can be scheduled with EDF can be scheduled with RMS? No. Any task that can be scheduled with RMS can be scheduled with EDF? Yes, that one's definitely true. EDF, if you can do it with EDF, then you can, EDF is more restrictive because it's static priority. So it's D. Okay, that's it. All right, so now, any questions? Okay, now I didn't review, make sure for your test you go back and look at your, the interfacing part of the class and the bit manipulation.
Yeah, you're gonna torture us with some of those bus protocols?
I might, yeah, there'll be a couple questions. Okay, quiz. Now, by the way, when it comes to those bus, just to be clear, those bus protocols, you probably will never design a bus protocol like that, but if you do any work with embedded systems or hardware, you will be using them. You'll use SPI and I2. They're very, yeah, they're very common. So the whole point is just understanding how they work. You should know how they work when you're using them, but you're probably not going to actually be implementing them. Maybe, or maybe you will, but probably not because there's so many off-the-shelf interfaces. One protocol that I regret not covering though is CAN, Controller Area Network, because that one is very commonly used in controllers and cars, and it's simple enough I could have covered it. You might say, well, if you're going to cover that, why don't you cover USB? That one's common. Yeah, but USB is really complex. I tried to, you would be shocked how complicated that one is. That's not that's a heavyweight protocol. That's not something that, I mean, I don't think I could reasonably even cover. It's more of a network protocol than it is the type of things that we're talking about, I squared C and SPI. But CAN, on the other hand, CAN is more similar to I squared C. And so I think next time I teach this class, I'll probably roll that in. But if you guys look at it, you'll be able to understand it having looked at those other ones. It'll be pretty clear. Okay, so I just want to finish the lecture on CMOS design. I'll review that real quick. I'm not going to get too far with it. I don't have that open already. Concepts. Yeah, so CMOS design. Okay, so we talked last time about semiconductors. So silicon is a semiconductor. It forms a crystal where the atoms form covalent bonds with 4 neighbors at different angles. So you create this like 3D lattice structure. Looks like this. It's kind of hard to tell from a, this is a 3D structure superimposed on a 2-dimensional slide. But you can see, I think there's 14 atoms in here that make up this structure, which is called the unit cell. It repeats infinitely. This is the smallest view of silicon that is kind of atomic. It doesn't repeat, right? The structure anyway. The problem is that this thing is 5 nanometers. This unit cell, right? And chips are down to 7 nanometers or 11, 7, 7. I think the TSMC. So the transistor size is smaller than this unit cell in modern chips. That's crazy, right? The atoms are only a 0.5 nanometer. The neighboring atoms are 0.5 nanometer. So can't go any smaller than that, right? Definitely, right? You got to have at least 2 atoms, I would imagine. But anyway, so the idea is that when you dope this thing, you're putting atoms inside the lattice that either have an extra electron or extra hole or a lack of an electron, and these act as charge carriers. These move charge. They move current through the lattice, and they make them more conductive. And so if you have, for instance, a diode, which is where you have p-type. P-type is with the holes, so that's from anything from group, you add a dopant from group 3, column 3. N-type silicon is add a dopant from row 5, right? And silicon is in row 4. You end up with these charge carriers, and so if you have a positive voltage on the P side relative to the N side, that positive voltage will attract the negative charge carriers in the N silicon, and the negative voltage, because there's a negative voltage of N versus P if you look the other way around, the negative voltage will attract the positive charge carriers, which ends up attracting them to the junction, right? And when they get attracted to the junction, they make this thing conduct from P to N. And likewise, if you try to send current the other way, it repulses them. And when you repulse the charge carriers from the junction, it cuts it off, so it won't carry current the other direction. Now, one thing I think I forgot to mention this last class, but in order for this to happen, you have to have the voltage over the threshold voltage. Okay, the threshold voltage is usually around 700 millivolts for silicon. If you have a Schottky diode, it's lower, but a regular diode is like 700. But the crazy thing about it, and something that sometimes people don't talk about, is that when you hit the threshold voltage, the apparent voltage over this it starts at 0 once you hit the threshold. So like if you have like a 1 volt potential difference, you have to subtract the threshold from that. So you have a 300 millivolt difference when you're actually putting a volt difference, right, on this thing, which is kind of crazy. But that's the way it works. So these diodes, then, you can build them into a transistor structure by, you have a substrate, which is usually P, silicon, and then you create little islands of N silicon that are the diffusion areas. And then in between is the channel, and then over top of the channel you have glass, an oxide layer, silicon dioxide, which is the same as beach sand, is silicon dioxide. And that is a insulator. It's an insulator. It has an insulation, the dielectric constant, which is the ratio of its permittivity relative to space, a vacuum. This thing has only 3.9 times the permittivity of a vacuum, right? So it's a very good insulator. And you end up with a capacitor here, right? So you have a capacitor where this gate is the top plate of a capacitor, and the bottom plate of the capacitor is the area between the diffusion area, right? Now, the crazy thing, I mentioned this last time, this is the part that's a little hard to wrap your head around, is that normally with a capacitor, it's pretty easy to figure out the voltage over the capacitor, right? You just have two plates and you look at the voltage difference, right? The problem is that when you turn the transistor on, the channel changes in a weird way because it attracts the minority carriers. So you put a positive voltage, and the voltage times the capacitance is the charge. So you put a charge on here. The charge creates an electric field. The electric field attracts minority carriers out of the substrate, which in the case of P is negative. Wait a minute, P? Negative? Yeah, because the majority carriers are positive. The minority carriers are the electrons, and they get attracted to the channel. But then you might say, okay, well then what's the voltage over this capacitor? Well, now we don't know anymore, because when you bring these charge carriers up into the channel, it decouples the channel from the substrate. So what ends up happening is that when current starts flowing from drain to source, current goes from drain to source, which is one diffusion area to the other. The voltage on the bottom plate of the capacitor is actually a gradient that starts at the voltage of the drain and ends up becoming towards the voltage of the source, right? So really what you're looking for here is what is the average voltage between the channel, the gate and the channel? What's the average voltage, right? So the capacitor is an average voltage over the capacitor. It depends on the electricity flowing through here, right? The problem is that if you ask too much of this transistor, if you ask it to source a lot of current, it saturates. And it does that because in order to get more current, because according to Ohm's law, if you want more current, you got to drop more voltage between the drain and the source. If you drop more voltage, then the average voltage because if there's a bigger voltage difference between these two sides of the transistor, the average voltage here starts to drop. It starts to be harder to get the gate up above the average voltage of the channel, because the channel has got this huge amount of current flowing through it, and so the voltage gradient is changing wildly, right? So what ends up happening is if you ask too much, it pinches it off and it saturates, right? Now you might say, why does that? Who cares? The reason this is relevant is because the speed at which circuits run on a computer chip, the whole clock speed, logic propagation delay, Moore's law, all of that depends on how fast this transistor can switch. And what you're really doing with these transistors is you're charging and discharging gates. The source and drain are charging and discharging gates of other transistors, right? Because this is a logic gate ultimately that's feeding into other logic gates, right? Because the logic gates have a capacitor on the gate, the job of this guy is to charge and discharge those capacitors as fast as they can. The faster it does that, the higher your clock speed is, right? Well, the problem is that how do you charge and discharge capacitors fast? You need more current, right? But the problem is you're limited in how much current these guys can send out, right? Because they have the saturation mode. And so that's really what drives really the entire semiconductor industry and computer chips and Moore's law. It all depends on how much current you can get through this guy, right? Ultimately so that's a very important thing about what computer engineers are doing when you're trying to make these things faster and more capable. Now another thing you could do also, you could reduce the capacitance here too. And you can reduce the capacitance if you make this smaller. You make the channel smaller, the area of the channel smaller, less capacitance, and thus faster switching. And that's what Moore's law is all about. But now, as I explained with that unit cell, we're pretty much getting, if we're at 7 nanometers, the dang atoms are only half a nanometer apart. You can't really get that much smaller. Okay, so we talked about that. So NMOS and PMOS is basically the gate controls whether the transistor is on or off. If it's on, drain and source are low, have a low resistance. If they're off, the drain and source have a high resistance. We talked about that even back when we were talking about SPI and the push-pull driver. It's the same thing as the push-pull driver discussion. NMOS has a 0 turns it on and a 1 turns it off. And NMOS is the more common sense one where 1 turns it on and 0 turns it off, right? But you can tell because there's a bubble. That bubble is an inversion, like you guys hopefully saw that in 211, the little bubble.
Why is the circuit symbol slightly different from the circuit symbols I'm using in electrical 371?
Because those are bipolar. So these are
for MOSFETs, not BJTs. But.
Well, these are MOSFETs. So MOSFETs, they're typically this symbol. BJTs are
Totally
yeah. Well, they're like angled. They still have They still have 3 terminals. Technically 4. That the body is the 4th terminal. Is not shown.
Actually, I forgot about the other 2 modes. The enhancement versus depletion mode.
Yeah. There's different. That's
why it's connected. Okay.
Yeah.
Forget the difference.
Yeah. The only thing about MOSFETs is that they don't show which arrow. They don't have an arrow to show which way the current's supposed to go. But it actually doesn't matter because these are symmetric devices. You can send current from drain to source or source. In fact, there's really no difference between this source. The drain and the source are conventional. Normally, you go from current goes from the drain to the source. And you might say, well, then why are they switched? Why is the drain on top there and the source is on top there? Because the NMOS is in the pull-down network and the PMOS is in the pull-up network. So they're on different sides of the power supply. That's why. Right? So in this case, that's usually the power supply VDD, and that's the output of the gate. Whereas over here, S is the ground and D is the output of the gate. So what's happening is that the function of this guy, just to put everything in perspective, is this guy is what's discharging the capacitors on the output of the gate. So you want to turn this guy on, and the current is going to roar back into the gate. You might say, well, it's an output, right? Yeah, even though it's an output, really you're sinking current. You're discharging the gate capacitance of your gates that you're driving through this guy down to ground. So you're going so you're discharging whoever's depending on me through my drain here, right? On this case, PMOS is going to charge up capacitors. And so in this case, I'm going to take current from the power supply through my source terminal, and I'm going to send it out the drain out to the gates I'm driving to charge up their gate capacitance to turn them, to turn them on. So that's the function. That's really literally what's happening here. So I have some quiz. I didn't have time to do a quiz, so I'm just going to give you a quick quiz here. Which dopant can be used to create a N-type silicon? Remember, N is the majority characters or the electrons. Phosphorus, boron, aluminum, gallium. You have to go back to the periodic table. I don't have this memorized. But basically, if you want N-type silicon, you have to pick something from, phosphorus. Yeah, phosphorus will do it. I don't know which ones they use. I think it depends on the fabrication, the fab. I don't know what they use these days. But phosphorus will do it.
We use boron and phosphorus a lot.
P-type would be, what type of silicon forms the body of a P-type? Okay, so a P-type transistor would have P-type source and drain, diffusion areas. The body would be the other type, right? So a P-type transistor would have an N-type body. Now, the problem is that you can't really change the body because the body is the chip, the actual substrate of the chip. So the way they do it is they create a well. So this is, the NMOS transistor has the chip is P, the wafer is a P, like the disc that forms the chips that you chop up and make chips with. The PMOS has a well that's a little localized area inside there of N. And then, of course, these all form diodes. Anytime you have a junction, there's a diode. Okay, yeah, so MOSFETs are defined as N-type or P-type according to their diffusion areas. Diffusion area is source and drain, not the substrate or the body. The body is the opposite type of silicon. Okay, then we talked about how to build gates. I love these gates because you build, you create a pull-up network and a pull-down network and use series and parallel connections. So in this case, this is a NOR gate, which means in order to send the output to 1 with a NOR gate, the only way a NOR gate is going to give you 1 is if you put 0, 0, 0 into it. So if I put 0, 0, 0, I get 3 zeros, I get 3 on transistors in series, and that'll connect the Y to the VDD. Any other combination of inputs will turn at least one of these PMOSs off, which will interrupt this pathway, and it'll turn on any of the parallel NMOSs on, right? Now the problem is that this is a problem because it makes it impossible. So question, what type of transistors comprise the pull-up network, or PMOS, P-type, and the pull-down network, or N-type? Now, I'm not going to have time to get into the reason for that. There is a reason for that. PMOS transistors are better at pulling up because of their charge carriers are more effective at that. But there's a consequence of that logically. The consequence is that if PMOSs are pulling up, I have to have at least one of them turned on to pull up, right? Which means that I have to have at least one input that's a 0 in order to get a 1 output of my function, right? Likewise, the NMOSs pull down. I got to have at least one input to get a 0. That's the problem because it means you can't make an AND gate and you can't make an OR gate. Because an OR gate, if you have an OR gate and you have a 1 on an OR gate, right? Or sorry, if you have a 0 on an OR gate, you have to put all zeros in, right? Right, but I need at least a 1 to pull it down to 0, right? So this is a more general question then. Which of the following Boolean functions can be realized with a single CMOS gate, right? So if you look at these functions, right, these are just ands and ors, but then I negate certain things. So the rule here is at least one logic, there must be at least one logic 0 input, which I didn't write, imply input. There must be at least one zero input when pulling up, and there must be at least one logic 1 when pulling down. Okay, so if you look at so there's 4 functions, and here's the 4 truth tables. So when you look at the truth tables, 1, that's fine, zeros, right? When I pull down, I got to have at least 1, 1, right? So yeah, all of these 0 outputs do have at least 1, 1, right? So I think this one checks out. This one's good. This one, number 2, this is fine. That's fine. That's fine. That's not fine. I can't have 1, 1 as an input and a 1 as an output. That's impossible. Because if I have 1 as an output, I got to have at least 1 0 to activate a PMOS in the pull-up network. I don't have that, so I can't do this function 2. Function 3, that one doesn't work. 0, 0 input, 0 output, can't be done. You have to have at least 1 input to turn on an NMOS to pull down to 0, so that doesn't work. And then function 4, that's good, that's good, that's good. 1, 1, no, that's not good. 1, 1 input, 1 output doesn't work because I can't turn on a PMOS because I need a 0 for that. So the only one that works here is function 1. So function 1, I can actually implement this, which is actually just a NOR. If used De Morgan's law, that's a NOR gate, basically. But these other guys I can't implement. Now I can still do them, but I have to create 2 gates, right? I can't do them as one gate, one CMOS gate.
Is that also why in digital logic, a lot of more advanced logic is made out of NORs and NAND gates?
Yeah, probably.
Because you can get the minimal amount of transistors.
Yeah, do it in one gate, yeah. Okay, let's see, how much time do I have here? Not much. Okay, so I briefly talked about these. Cutoff is when the voltage of the gate is below the threshold. Linear is when the gate acts like a resistor, meaning that the current scales with the voltage, right? It follows Ohm's law. Okay, but then saturation mode is when you don't follow Ohm's law because this guy will turn into a current source. So when you're in saturation mode, the amount of current flowing through the transistor is fixed. So it becomes like when you guys took circuits, it's like an independent current source. But the problem is it depends on the mode that you're in, and this gets complicated because the mode depends on the drain source voltage, that's how much current you're trying to get from the transistor, as well as the gate voltage, right? So it gets kind of complicated. So this slide, I'm not going to have time to do this, but this goes through all the mechanics of how it works. But basically, the thing to understand here is that the current, and again, you want to maximize the current for speed. It's a charge over carrier time, and the charge is, as I mentioned, charge is capacitance times voltage. The capacitance is a function of the width and the length of the channel, so just the 2D area, divided by the thickness of the oxide. How do you change that? Well, that's something that goes down with Moore's law too, generally. You shrink, you make the oxide layer thinner and thinner and thinner because you want that to be thin. Dielectric constant, well, I think they've always used glass. I don't think there's anything better than glass on Earth anyway. I mean, a vacuum would be 3.9 times better than glass, but I don't know if we got anything better than that for dielectric constant. In other words, how insulating it is essentially, how good of an insulator. Carrier, okay, blah, blah. Anyway, the point is that the width and length are important. Those are the only things that we can control. We can't control the oxide thickness. We can't control the dielectric constant. The only thing, we can't even control the carrier mobility, the materials, the doping amount and all that defines how fast the carriers move. The only thing we as designers can change is the W and the L. So we have to be able to adjust the width and length accordingly. So in general, you want the width to be minimal because the width, I'm sorry, sorry. The length is minimal. The length is how far the carriers have to go. And so the time it takes to switch the transistor depends on the velocity of the carriers, which we can't change, but we can change the distance they have to go, which is the length of the channel, right? So that's when they talk about a 7 nanometer process and 11 they're talking about the length. That's the channel length. The width, on the other hand, is something we don't want to necessarily use minimal size all the time on. I mean, if we make it minimal, then the transistors are minimal size and we could fit more of them, right? But if you make the width bigger, you get more current because you got let me show you, let me back up here because I think this is an important point. If you go back to the three-dimensional view here, right here. Okay, so this is the length. So we're only showing the length here. If you look at the three-dimensional, there's the length, right? This should always be minimal. There's no reason to not make the length minimal because we want to get those charge carriers across as quickly as possible because then it switches faster. The width is this part. That's how deep the transistor is. The deeper you make it, the more charge carriers are going across in parallel across the channel. And therefore, the more current you can get across, right? So if you need a transistor that has more oomph, more power, then you increase W, right? Now, actually, you actually don't increase W because the way you lay out chips, you have a limited space for these things. So what you end up doing is you increase the width by making multiple parallel transistors is the way you do it. So you can make width bigger virtually by having multiple parallel transistors that are all contributing charge carriers at the same time. You get more power out of the transistor, and thus it'll switch faster for a larger load. So if you're going off chip, like you do with SPI, you're going to have a giant transistor. If you're on chip and you're just going short distances on chip, then you don't need much. But the bigger you make that W, the more it'll amplify, the more gain you're going to get. Okay, so okay, so W, so the length and width. Skip this for a minute. Last thing I want to talk about. Okay, so you might, okay, so the speed of these guys is determined by these capacitance and resistance. So there's a capacitor under, that's the gate. We already talked about that. But one thing I haven't talked about yet is there's also capacitors in the diffusion areas. Because as it turns out, a diode that is reverse biased, meaning that the voltage of the cathode versus the anode is positive. That's a reverse bias diode. It won't send current through it, but it will create a capacitor. Because what happens is when the charge carriers are repulsed away from the junction in the diode, that area between the charge carriers and the junction becomes the middle part of a capacitor, the insulator part of a capacitor. So you get capacitance here. This turns out to be really significant because these guys have capacitors. And remember I mentioned that with a logic gate, it's the source and drain that's actually driving the output of the logic gate. The gate is the input of the logic gate. So the capacitance you get from gate to gate starts at the source and drain, and then you connect to the gate, which is the input of the next gate downstream, and that has a capacitor too. So you have to add all that capacitance up. Meanwhile, the transistor, when it's on, it also has a resistance, an effective resistance. When a transistor is on, it's basically it acts like well, in linear mode, it acts like a resistor, right? And it's always in linear mode, by the way, except when it's transitioning when you're going from 1 to 0, when you're going from 1 to 0, 0 to 1, it's in a saturation mode right in the middle. Because what ends up happening is as you switch a gate from 1 to 0, 0 to 1, you're doing temporarily shorting out. Because for a while, both the pull up and the pull down network are on at the same time. And you'll end up getting into saturation mode briefly. But after you settle, then you're in linear mode, right? In which case the transistor becomes a resistor, basically. Okay, so what is my point of this? So you can create this RC delay model. So if you have one NMOS transistor, you have a capacitor from the source to ground, from the drain to ground. Why? Because the substrate is grounded. That's the substrate, the bulk, the base of the body is grounded. And then the gate has a capacitor, right? Does that make sense? Likewise, with a PMOS, same thing, except the other side of the capacitor is connected to the body terminal, which is now charged up to VDD, right? That's the well, right? Okay. So what's surprising about this? Well, this is the RC model of a transistor. You turn the transistor into a resistor when it's on, right? So there's the resistor, and the capacitors. But then, depending on the size of the transistor, which is your width, that is going to change the resistance as well as the capacitance. So when you make a transistor wider, you decrease its equivalent resistance, but you increase the capacitance. So you kind of screw yourself over a little bit. It's kind of contradictory, right? So you're adding capacitance, which is bad, but then you're lowering the resistance, which is good, right? So you have to take into account the size of the transistor. Okay, well that's all I have. That's about as far as I'll get for today. Any questions?